Welcome back. So we have been looking at recurrence relations and how to solve them. In this next set of video lectures, we will see one more technique of solving the recurrence relation, and in fact this is one of the most powerful techniques that is there for solving recurrence relations. So to start with, let's recap. The recurrence relations, we mean a sequence of numbers where the initial set of them are given while the nth term is written as a function of the previous terms. Recurrence relation is used extensively in combinatorics, analysis of algorithms, and various other subjects. We have seen that recurrence relations can be used for modeling problems, particularly counting problems. And the question now is that how do we solve recurrence relations? So we have seen a few of the examples of recurrence relations, and for some of them we have seen techniques of solving it. Now to quickly recap the technique that we have, the first one was you first guess the solution and then prove using induction. Now this technique works perfectly if you can guess the solution correctly. Once you guess the solution correctly, proving it by induction is quite a simple step. But sometimes the question is, how do you guess the solution? The technique one that we did for guessing the solution was by unfolding the definition. And we saw how by unfolding the definition, one can try to guess the solution correctly. But then there are some particular class of functions or recurrences where guessing the solution is not easy. For example, this particular expression for the Fibonacci sequence, where you cannot guess it mainly because I'm telling you the final form of it, which is this, and there is no way we can guess it or understand it by unfolding the definition. Similarly, we have the other techniques where we have some more complicated expressions which doesn't yield a very nice formula that can be guessed. In the second case, when there doesn't exist a very nice formula, what we told is that many times we can possibly come up with some upper bound and lower bound. And once we can come up with the upper bound and lower bound, we can use various notations, asymptotic notations, to basically give a compact form for it, which in many times is good enough for us. So we have seen the rotations of big O, big omega, theta, sim, small o and small omega. And this is not only, this particular way of comparing functions is not only useful for solving recurrence relations, but is also used for other things also. And using this, we could solve examples like this where we don't have a very nice solution, but we can come up with some nice upper bound and lower bound. The technique there was, you first guess the mn for some nice enough integers n, in this case for power of k, and then by induction prove that this value mn is theta of n log n, whatever you have guessed here. And it is done by first proving an upper bound and then proving a lower bound. So this is the second technique that we have. First technique, when we can guess the formula for the recurrence exactly, that we can do possibly by unfolding the definition. Second technique was when we can not guess it exactly, but we can prove a theta notation or some obligo notation and so on, which indirectly means that we can prove a upper bound and a lower bound. And we saw that there is some master theorem which can help us to guess the solution easily for us, depending on some of the things. But still, we have certain recurrences for which we still don't know how to solve them. For example, this one, the Fibonacci number. f0 equals to f1 equals to 1 and fn equals to fn minus 1 plus fn minus 2. Now, how do you guess the fn? How do you even come up with an upper bound or lower bound? And in fact, I had told you, this is something I'm telling you beforehand, that this function finally does come down to this expression. Fn equals to 1 plus square root 5 by 2 power n minus 1 minus square root 5 by 2 power n by square root 5. Just by looking at the expression, you can imagine that this is not a trivial or not an easy recurrence relation to solve. In the next set of video lectures, we will show you how to attack this problem. And by doing so, we will come up with a very generic technique of solving this particular recurrence. As I told you in the beginning of this video, it is a very powerful technique for proving it and possibly a bit complicated technique also. So we will go a bit slow here. Now, for this thing to work, we will define what we call as generating functions. So let's start with a sequence of numbers, a0, a1, a2 till whatever, a infinity or some value. Now the generating function is basically this polynomial that we define, where x is a variable and p of x is a polynomial defined as a0 plus a1x plus a2x square plus a3x cube and so on. Right? So in other words, p of x equals to summation of ai x power I, sum over all, this is I of course, for all I. Now this is what we call as the generating function for the sequence. Now this doesn't solve anything. I am just representing this generating function as a polynomial. But maybe using some nice tricks that we will see in the next video, we might be able to somehow compute the nth coefficient, meaning the coefficient of x power n in this polynomial px. And if I can do that, then I will understand that the coefficient of x power n is nothing but an. So I will get a formula for an, which in fact would be the solution for the recurrence relation. Now this step is clearly not very obvious. How do you get it? I have defined a polynomial which at this point is nothing but an abstract polynomial, because I don't know this a1 to a0 to a infinity, all of them, right? If it is given the recurrence relation, all I know is the initial set and the final in some, and the a in terms of the earlier ones. But abstractly, I can think of this polynomial, and the goal will be to somehow get this polynomial and understand the coefficient, the nth coefficient of x power n in this polynomial. Now this is the overall idea. We will see the application of this one next video. In this video, we will take a small detour to see something what we call as a generalized binomial theorem. We will need it for what we will do next class. So let's start with the binomial theorem. We have done it during the time of counting, and we have basically this statement that for all n we have 1 plus x power n equals to sum over k equals to 0 to n choose k x power k. Now the important thing is that what is n choose k? Okay, I'll come to that. Before that, the important thing is that n is a natural number, so something like 0, 1, 2, 3, 4, 5 and so on. In this binomial theorem, I don't know what it means when n is equals to minus 1, because this number n choose k is not defined for n negative, or if n is not integer. Of course, from this binomial theorem, I can put other values in x and I get something like this. 1 minus x equals to sum over k equal to 0 to 1. 1 minus x power n equals to summation k equals to 0 to n minus 1 power k choose k x power k. But again, I need the fact that n is a natural number, right? Now, let's try to understand what does it mean by this n choose k. So the n choose k is nothing but n factorial by n minus k factorial times k factorial. Which means that, so n factorial is of course n into n minus 1 into n minus 2 till 1. N minus k factorial is n minus k into n minus k minus 1 and so on till 1. So if I divide this n factorial by n minus k factorial, I get something like this: n into n minus 1 into n minus 2 till n minus k plus 1 divided by k factorial, which is k into k minus 1 into k minus 2 till 1. Now, if this is the definition of n choose k, let me tell you a pretty ridiculous looking theorem which is known as the generalized binomial theorem. And this is that even for n equals to n in real number, I have the same expression. So 1 plus x power n equals to k equals to 0 to n choose k x power k, where now since n is not necessarily natural numbers, I have to define what this n choose k is, where n choose k is not this but this. Why is it not this? Because if n is not natural number, say n equals to minus 1, then n factorial doesn't make any sense. But this makes sense. I can define if n equals to natural number, I know what n is, what is n minus 1 is, what is n minus 2 is, and I can go on till n minus k plus 1. So this is in fact a proper definition of n choose k. So in other words, I claim that there is this theorem called generalized binomial theorem, where for all n which is in any natural number, positive or negative, I can prove 1 plus x power n equals to summation of k equals to 0 to n choose k x power k, where n choose k is defined as n into n minus 1 into n minus 2 till n minus k plus 1 divided by k into k minus 1 into k minus 2 till 1. Now, let me leave it to you guys to convince yourself that this statement is true. For people who are interested in getting the proof of this, I encourage you to take a look at the internet or solve it yourself. The proof is not hard. It can be done using induction. So in fact I will say that prove this theorem when n is the integers, meaning when n equals to -1, when n equals to -2 and so on. And you prove this statement. And you will see that you will be able to prove this statement. For n equals to integers, then you have to prove for n equals to rational, and then finally you have to prove n equals to n is for reals. So I will not give you the proof of this statement, but I will show you how this statement can be applied to get some outstanding nice things. So this is the statement that we have. You can of course strike out this thing. So that is not what it is. N choose k is this. Now let's try to see what happens to 1 plus x power -1. Now to understand it, let us first understand what happens to the first coefficient, right? So this will be k equals to 0. If k equals to 0, then what is n choose k? So the n choose k is, how many terms are there? There will be k of them. Now if k is 0, then the bottom one is 0 factorial, which is 1, and the top one will be nothing, that is 1. So I get 1 here. What is the coefficient of x? Coefficient of x has k equals to 1, right? So the bottom one will be 1 factorial, and the top one will be -1 into -1 minus, now can I have anything else? No, I just can have only one term, right? So I will just have this -1. So the next one will be nothing but minus x. What will be the next one? If k equals to 2, then the bottom one is 2 factorial, which is 2, and the top one is -1 into -1 minus 1, which is -2, which is of course, say sum them up, it is 1, so this will be plus x square, and so on. And you can see that what you will get finally is that 1 plus x power -1 is 1 minus x plus x square minus x cube, and so on, which is of course summation over n minus 1 power n x power n. Very similarly, if I can, here only I can replace x with minus x, I will get 1 minus x minus 1 as 1 plus x square plus x cube, and so on, which is this. So in other words, this generalized binomial theorem is helping me to write down something like a polynomial like 1 plus x power -1, or 1 plus x plus x to the power -1 as a polynomial over x without any reciprocal. This is what is known as the Taylor series. Similarly, for 1 plus x power -2, we can write down an expression like this. This is what is known as Taylor expansion or Taylor series. And we have the Taylor series for quite a number of them. As we just now saw, 1 plus x power -1 is 1 minus x plus x square minus x cube, and so on. Similarly, 1 minus x is 1 plus x plus x square, and so on. From this we can also get something like this form, 1 minus ax as 1 plus ax plus a square x square plus a cube x cube, plus so on. We can also have something for like 1 plus x power half. And there are also Taylor series for things which are not polynomial, like e power x, which is 1 plus x square by 2, and which is basically sum over x power n by n factorial. So these are called the Taylor series expansions for functions which are not necessarily polynomials. So most functions that you have can be written as a polynomial or in the Taylor series expansion. We will use this particular idea to see how we can use the generating function for solving things like the Fibonacci number, recurrence, and so on. We'll do it in the next class, next video. Thank you.